I think everybody got into WebAssign. I think there was maybe one person did get into WebAssign. So hopefully those issues have all been resolved. That was a pain in the butt. Not how I wanted to spend my Wednesday trying to figure out what the hell was going on. But that's all right. Again, I want to remind you do have a homework assignment in WebAssign due on Sunday over the first section. If you've got questions, I'm happy to answer them. But remember, don't use the Ask Your Instructor button, right? Take a screenshot of the question and email me directly. Because for some reason, Cengage doesn't like my email. I don't know why. It comes in like 4 days in. So just a reminder, if you've got questions about WebAssign, happy to answer them. But just make sure you just email me directly rather than asking your instructor through WebAssign. Because it just isn't going to, it's not going to work for whatever reason. All right. Any questions at all over anything before we continue on with what we were discussing last time? All right. Well, let's go back into it. So we were talking about domain and range. Talk a little bit more about that today. Finish up with the net changes at the end, and then we'll get into doing some graph stuff with functions. So remember, again, domain is the set of things that you can do what? What's the domain? What are we interested in? What you can put in, and the range is what you get out, right? All right, so this function is h of x equals 5 minus absolute value of x. Remember, again, absolute value of x basically just you put in a number, it takes away a negative if there's a negative sign, right? All right. Any issues doing that at all? Any domain issues at all? No. So what's the domain going to be for this one? All real numbers, and an interval notation again we use. Yeah, so we'll use that minus infinity to infinity with parentheses on either side. Remember, right now there's two big issues that we need to worry about for domain. Can we possibly divide by 0? Can we take the square root of a negative? Right, those are the two big things that we have to worry about right now. We'll see some examples of that here in a minute. All right. So for absolute value, again, we said absolute value does what? It basically takes away a negative if there is a negative, right? Otherwise, it just leaves it alone. So what's the smallest thing that you could possibly ever get out of an absolute value? 0, right? The smallest thing you could ever get out of absolute value is 0. Right? So notice that we're subtracting things, right? If we subtract things that are getting bigger, then the answer gets smaller, doesn't it? Okay. So looking at this 5, if the smallest this ever can get is 0, what's the biggest 5 minus that thing could ever get? 5, right? So what's your range going to be then? So 5 is the absolute highest you could ever get. Good, yep, good. Negative infinity to 5. And then am I going to use a parenthesis or a bracket on the right-hand side? A bracket, because we can actually hit the 5, right? And I think we'll see a little bit better for the range when we start looking at graphs. I think it'll make a little bit more sense. Rather than having to try to reason through it every single time, we'll be able to look at a graph and see what's going on. Is that okay? All right. So in the next few examples, we're just going to concentrate on domain. We're not going to work on range because it's a little bit harder to try to reason through them. We should be able to understand what we mean by domain, what we're allowed to plug in. Range, we'll leave that to looking at a graph if we want to, which we're not going to do today. All right. So let's look at this one's asking us for the domain of f of x equals x plus 1 over 2x minus 3. I just mentioned a minute ago, what two things do we worry about right now for domain? Divide by 0 or root of negative, right? Square root of the negative. Looking at this one, what might there be a problem? Divided by the 0 piece, right? Okay. So if I look at that 2x minus 3, if I set that equal to 0 and solve for the x, what do you get? Yeah, so it would add the 3 over and then divide by the 2, right? Do we want to plug this number in for x, or is that the one we want to avoid? We want to avoid this one, right? Okay. So again, if I want to try to talk about writing my domain, I want to write it in interval notation. If I want to avoid that number, I would have an open circle there on my number line, right? But I could put in anything else. So I could go off to the left forever, or I could go off to the right forever, couldn't I? So if I want to put this in interval notation, how would we describe just this part? What would we write down to describe just that part? Okay, negative 350 to 3 halves. And then would I use a bracket or a parenthesis? Yeah, parenthesis because we don't want that one, right? Okay. What interval would you use for that side? Good. And again, we would use parentheses, right? Now I'm going to put something in the middle of these as well. But are we okay with where we're getting these intervals? Right? So that's why I drew the number line, right? For this left-hand side here, this is my right endpoint. I don't have a left endpoint, so that's why we're using negative infinity on that side. And then putting parentheses around it. Same thing on the right-hand side. Are we okay with writing those intervals? Because you're going to be expected to be able to write your answers this way. Is okay? All right. Now, to be in the domain, I can be in this side, or I could be on this side, right? The way we mathematically describe the word or is what we call a union. And so we use a little symbol in between them that looks like a U. That union symbol there just means to be in the domain, I can be in this interval, or I can be in this interval. That's what that union symbol means, is an or. Is okay? Right. Again, I'm not worried about range on this. Range would be a little bit more complicated. We'll see range of these things later on. This type of function is referred to as a rational function, and we'll play with rational functions in chapter 3. All right. Let's look at the next example. We've got g of x equals square root of 14 minus 7x. What can go bad here? A negative under the radical, right? We don't want a negative under the radical. Right? Okay. So we want that 14 minus 7x to be greater than or equal to 0. That's what we want. That's what we need in order to be in the domain. So if I want to solve for x here, we would subtract your 14 over. So you'd have negative 7x is greater than or equal to negative 14. Then divide by negative 7. I have an x on the left-hand side. I've got not a negative 2. I've got a positive 2 on the right-hand side. What do I do with that inequality? I got to flip it because I divided by a negative, right? Remember, if you multiply or divide an inequality by a negative, it flips the inequality. So this says my x needs to be less than or equal to 2. So how would I express that in interval notation if I need everything less than or equal to 2? Okay. Okay, so negative infinity to 2 it definitely is true. What am I going to put on here for my... this one's going to be a parenthesis. That'll be a bracket. Right? Because it says equal to. Now notice if it gets bigger than 2, it's going to make that negative. So in this case, I won't have the right-hand side. So I just have that negative infinity to 2 in this case. See if you can work on that third one for a minute. Think about it. Then we'll chat about it. We ready to talk about this one? Okay. So again, what are the two big things we need to worry about for domain? What are the two things to look for? 0 on the bottom, negative under the root. This one's got both of them, doesn't it? Possibilities, right? I've got a square root in the denominator. Okay? So what do we need to make sure happens? What needs to be true about this 6x minus 18 piece? What do we need to make sure happens? It has to be greater than 0, right? It can't be equal, can it? If it's equal to 0, then it makes the denominator 0, right? So we need to make sure that what's underneath the radical in this case is strictly greater than 0. Can't have the equal sign on this one. If we solve this inequality, we'll add the 18 over and then divide by 6. Do I need to worry about flipping the inequality this time? No, because it's a positive that we divided by, right? So we should have x is greater than 3. So now we want to express this in your interval notation. What would you write? Good. Yeah, so we'd have a parenthesis on our 3 in that case, and then an infinity on the right-hand side. Not a bracket this time because we can't have it equal to 0 in the denominator. That okay? All right. So let's shift gears a little bit and talk about net change. Later on, we'll end up talking about average change. Okay. But we'll talk about net change here. So say you started on a trip and you were 10 miles from here to start. So you're 10 miles from here. And you ended up at a place 40 miles from here. How far did you travel? You started 10 miles from here and you ended up 40 miles from here. How far did you travel? 30. How'd you figure that out? Yeah, 40 minus 10, right? You did where you ended up minus where you started, correct? Okay? That's exactly how you calculate average change, or excuse me, net change. You're starting at x equal to c, you're ending at x equal to d. If I want the net change, I'll plug in d into the function, I'll plug in c into the function, and I'll subtract. It's where you ended up minus where you started. That's it. Okay. That's how you calculate net change. All right. So we look at this first example. If you want the net change from -1 to 4, what number do we plug in first? The 4 goes, right? That's where you ended up, right? So we want to do f of 4 minus f of -1. What do you get when you plug in 4? You get 17, right? You get 5 times 4 minus 3. What do you get when you plug in -1? Good. So 5 times 4 minus 3 gives us the 17. 5 times -1 minus 3 gives you -8. And this is why I'm using parentheses. It really is minus a minus, right? It's minus -8. So if you simplify that, you get 25. Okay. But that really is all there is to it, to do a net change. So you tell me how to do the next one. Yep. The function name in this case is g, but that's the right way to do it. We're going to do g of 5 minus g of 2. Which one is? 5 squared minus 2 times the 5, right? Because I got to put the 5 in the x for that one too. Yep. And then the other one's going to be yep, good. Yeah, the first one is 5 squared minus 2 times 5, right? Because we're taking out the x and putting in the 5, right? The other one, we're doing the exact same thing, except with a 2. What do you end up with when you're done? Well, 5 squared is 25 minus 10, right? That one's 15, and the other one is 0. That one's 0. Yep, I agree. So we get 15 when we're done. Is okay? We will come back to this idea of being able to do these net changes idea when we come back to average change, but that's what net change is. All right. All right, so we're going to move on to the next section here. By the way, your web assignment homework is over that first section. Okay, so that's what we do on Sunday. So this stuff that we're talking about now is not on the web assignment that's due on Sunday. All right. All right, so what we're going to concentrate on in this section is basically getting a library of graphs, if you will. Just to start with, that's what we're going to be interested in. Is getting like what we're like I like to think of as a library. One of the best ways to figure out what a function is doing is to look at its graph. Tells you where it goes up, tells you where it goes down, tells you if it's increasing quickly, if it's going up fast, does it go up slow? Does it turn around? Are you at a high point? Does it bottom out? Are you at a low point? Okay. Getting a graph of a function is helpful in understanding what's going on with the function. Okay. Gives a nice visual representation. So we want to spend some time talking about how do we get the graph. So again, we think about functions. We plug something in, we get something out, right? So for our purposes, the things that we're going to plug in are going to be our x coordinates. How far left or right are we? The things that we get out will be our y coordinates. Okay? So the graph of the function is the set of ordered pairs. We'll say x comma f of x. Oops. Plug in an x, get out an f of x, where your x is in the domain. And I just refer to the domain as D. Okay. So one of the first things you probably want to try to do, at least in your mind, is equate the function value, the output, with a y coordinate. Okay? The output is a y value. All right. So we're going to be to start with, we're going to be very, very rudimentary with how we get graphs. Okay. We're just going to plug some values in for x, pick some values for x, plug them in, and get some values out for y, and plot some points to start with. Okay? So we'll start making a list of points here. Pick some negatives, pick some positives. So I'll do -3, -2, -1, 0, 1, 2, 3. We're literally picking these. I just picked integers here. I'm going to pick fractions. Nothing was special about the numbers I picked, except that it'll be a little bit easier for me to figure out what the numbers are when I get out. Okay. Again, when we plug in the value, our function is just x cubed here. So I'll put the -3 in. and then we will cube it. If I do -3 times -3 times -3, what do we end up with? -27. Do the same thing with your -2. What do you get in that case? -8. We do it with -1, we get -1. What do you get when you put in 0? You get 0, right? Because 0 cubed will be 0. When you plug in 1, you get 1. Plug in 2, we get 8. Plug in 3, we get 27. We get the positives, right? Everybody okay with those? All right, so now we want to graph it. Pardon me. Might want to change the scale maybe a little bit because these are really close together, but it doesn't really matter. So if I want to graph this thing again, I'm going to plot the points, right? -3, it'd be my x coordinate. -27 would be my y coordinate. I fall way off the graph, right? So I'm going to not plot that one. But do -2 and then -8. 1, 2, 3, 4, 5, 6, 7, 8 would be down here. -1, -1, left 1 and down 1. Zero, 0 is the origin here. Plot 1, 1, right 1 and up 1. 2, 8, over 2 and up 1, 2, 3, 4, 5, 6, 7, 8. And again, if I put in 3 and get 27 out, I'll be way off my graph, right? Okay. So again, we just took our values here. So we took our ordered pairs here and just plotted the points. Now, again, we used integers when we plug these things in, but there are pieces that are missing, right? We can put any fractions that we wanted. Our domain here is all real numbers. So we want to fill in the gaps, and we want to do it what I'll refer to as smoothly, right? I don't want to make just line segments, okay? I want to make it nice and curved if I can, okay? So we'll just fill in the gaps that way. Go up, it'll flatten out, and then it'll go up again and go off to infinity that way. And again, the idea here is to help us get a library of functions, what these things are looking like. So one of the things that you might be wanting to think about is this kind of basic shape, this S-shaped curve. Notice it's going from lower left to upper right. And notice that our power here is a 3 in this case. Okay. Let's look at the next one, where we've got x to the 4th. Might change my scale a little bit just so we can get a few extra points on here. Notice I'm going to not do as many points this time. Let's just do -2, -1, 0, 1, and 2. What do you get when you take -2 and raise it to the 4th power? You get a positive 16, right? This is one of these to make sure you're careful on your calculator if you're using your calculator to help you. Notice that the -2 is going in for the x, so I have to do the -2 to the 4th power. If you were to type in a -2 to the 4th, like this on your calculator, it's going to give you -16. I think I mentioned this the other day. Remember, your calculator knows order of operations, right? Exponents go before multiplication. This you can think of as times -1. It would do 2 to the 4th and then multiply, right? I want to make sure I would put parentheses around that to make sure you get a positive 16. Okay? So be careful with that. What do you get when you put in -1? get a positive 1 in this case, right? Put in 0, we get 0. Put in 1, we get 1. Put in 2, we get 16. Notice in this case, we're only going to ever get positive numbers out, right? All right. I'm going to change my scale a little bit on my y's just so I can actually plot this a little bit more. Okay. I want to make my y's go up by 2 and my x's go up by 1. So negative 2 will be a positive 16. So 2, 4, 6, 8, 12, 14, 16 will be here. Negative 1, 1 would be here. Or, sorry, I went up too high, didn't I? I said I made a scale of 2. It would be there. Would it be halfway in between? 0, 0, 1, 1, and then 2 positive 16 would be there. Is okay? And then again, play or connect the dots, but do it nice and smoothly. We should be flattening out and then going up that way. And again, what we're really interested here isn't so much exactly where the dots are. It's right now we're more interested in what does the shape look like. All right, so again, going back to the previous one, notice that the previous one went lower left to upper right, and notice that their power was a 3, right? This one, what happened? It made a U shape. Our power was a 4. Okay, let's think about why it's doing that. Remember when we do the cube and we put in negatives, we do a negative times a negative makes a positive, times another negative will make it negative again, doesn't it? That's how we ended up on the lower left-hand side. Fourth power, it did negative times negative was positive. Another negative times negative was positive again, right? We ended up with a positive. So if I had, instead of x cubed, we had x to the 5th, do you think it would look like the first one or the second one? First one, right? Because it's an odd power. You'll multiply a negative times itself an odd number of times, you end up negative again, right? If we had, say, x to the 10th, does it look like the first one or the second one? The second one. This is an even power, okay? So if I have just a single x to an odd power, it should look like this first one. If I have a single x to an even power, it should look like that second one. That's the kind of things that we want to pay attention to. Is this okay? Yeah. Same idea, but now let's kind of flip it upside down. Let's look at this y equals 1 over x squared. First thing you should notice is that this one's going to have an issue. Where is this one going to have an issue? Only dividing by 0, right? So what do we not want to try to plug in? 0, right? Because that'll make the denominator 0. Okay. So in this case, let's pick up a couple of points, but not 0. Let's say I pick -2 and -1. We know 0 is not going to work. Let's do 1 and 2. We might want to plug, we're going to plug some more in than this, but let's just start here. Okay. This says to do 1 over -2 and square it, right? What do you end up with when you do that? Good. 1 over 4? Yep, I agree. The next one is 1 and divided by -1 and square it will give me just a 1. Right? I'm going to get the same thing if I put in 1. And if I put in 2, we also end up with 1/4, right? You agree with that? Now notice if I put in bigger and bigger numbers, what happens when you start dividing by bigger and bigger things? What happens to your fraction? If you divide by bigger and bigger things, the fraction gets smaller and smaller, right? So if I put in like 3, I would get a 9th. If I put in a 4, I would get a 16th. It just gets smaller and smaller and smaller and smaller, right? That doesn't tell me much of what's going on in the middle, right? If I just plot these points so far, I've got -1, +1. I've got -2, a fourth. +1, +1, +2, a fourth. Something like that, don't I? But what's going on here in the middle? I don't really have anything in there, do I? Okay. So let's try to put in a couple of fractions and maybe that'll help us see what's going on in the middle. Okay. Not a whole bunch, but maybe we'll put in, let's put in a half, -1/2, and I'll also put in a +1/2 because that'll be on the other side. And let's do -1/10 and +1/10 to see if we can figure out what's going on a little bit. We square the negative, it becomes positive, right? 1/2 squared is 1/4, but it's in the denominator. If you do 1/4, what do you end up with? I do 1 divided by 1/4. What do you do? What do you do when you divide by a fraction? You flip it, right? Yeah. So when I do 1 divided by a fourth, I would have 1 times 4, wouldn't I? So I end up with 4. I wrote a 1, sorry. I can fix that quickly. Right? Remember, dividing by a fraction, you multiply by the reciprocal, correct? So if we're dividing by a fourth, we'll multiply by a 4. So what do you get when you plug in +1/2? You know, let's get a 4, right? Because all we did was just square the 1/2, didn't we? Okay. So notice if we plot those points, I go either left or right a half. I go up to 4. So there's a point up here and a point up here. What would you get if you plug in a 10th? Either positive or -1/10. When you square 1/10, what do you end up with? 1/100, right? It'll be positive because we're squaring the negative, correct? Right? And the same idea, we multiply by the reciprocal, bless you. So dividing by 100th is the same thing as multiplying by 100. We get something big, don't we? We get the same thing for the other one. Now, I can't really plot my graph. I can't plot those points because it'd be way off my graph. But it should give you an idea of what's going on. If I start drawing my graph in towards the y-axis, what's going on? It's going to go up, right? Go straight up the line. Exactly right on either side, isn't it? What's going to happen out here? We said as we divide it bigger and bigger, we get smaller and smaller. It's going to get really close to the x-axis, isn't it? So when we draw this now, we'll go up like this and down like this. And that gives us a rough graph of that what it looks like. That okay? So notice that 0 we said was a domain problem, right? Trying to divide by 0. Notice we get this graph shooting up when we try to get really, really close to 0. We refer to this as a vertical asymptote. We also refer to this one as a horizontal asymptote. We refer to that as a vertical asymptote, and that happens a lot of times when you try to divide by 0. The graph will end up with an asymptote there, a vertical asymptote there. And like I said, we're going to talk about rational functions in chapter 3, these things that we're doing divisions. Okay? And we'll do that. We'll talk about asymptotes a lot there when we get to that. Okay. So if we look at the next example, we would anticipate again that we're going to get a vertical asymptote there at 0 again, don't we? Now, what do you think is going to happen? Just by the knowledge of what we did before, by the way, by the previous one. Notice that when we had that odd power, we had this piece that was below the x-axis on the left-hand side. But when we had the even power, notice that we weren't below the x-axis at all, right? Do you see a similar thing here? I've got an even power. Everything's above the x-axis. What do you think might happen before we even start? What do you think is going to happen with this one? Yeah, there's part of it's going to be flipped, isn't it? Most likely. Okay? Just like it was over here, isn't it? Notice that we have the odd power here. This kind of left-hand side is flipped upside down, isn't it? Okay. So we kind of anticipate the same kind of thing happening because we have an odd power here. Right? Just to verify that that might really be what's going on. Oops. If I put in -2, what do we get out? Good. Put in -1, we get out -1. So if we put in +1, we'll get out +1. If we put in +2, we'll get out +1/8. Right? So again, if we plot those points, there's a -1. There's a -1/8, a +1, a +1/8. And again, same idea. We anticipate this looking a lot like the previous one, except the left-hand side should be flipped, right? We still should expect that vertical asymptote at 0. We should expect that as you get bigger, the graph gets closer and closer to the x-axis. But the left-hand side here, instead of going up, like the previous example did, it's going to go down this way. And this one should go this. Whoa, hey, I missed. And we get this kind of shape. These types of functions where you've got 1 over x to a power, an integer power, positive integer power, we refer to those as reciprocal functions. We would expect all the reciprocal functions to look like one of these, depending on if the power is even or odd. So asking questions like I asked before, if I had 1 over x to the 6th, would you expect it to look like this graph or the previous graph if it was 1 over x to the 6th? The first one here, right? Like that one because it's even. If you had 1 over x to the 5th, you would expect it to look like this one because it's odd. That makes sense? Okay. Again, that's the whole point of this process, by the way, is to help us build up a library of things to give us an idea of what things might look like if we see something new to fit into the patterns that we've already talked about. Questions on either of those? Okay. All right. Let's do a couple of other functions. Notice we've done the first two types of or examples of power functions. Then we did reciprocal functions. Now we're putting things with radicals in them. We refer to those as root functions. Okay. So the first one is square root. Again, when we have square roots, what do we worry about for domain? Negatives, right? So I don't want to try to put any negatives in here at all, okay? So if I want to pick some values, I'll start with 0. I guess I have y's as opposed to f of x's, but that's okay. I'll start with 0, and this time I'm going to be a little bit more strategic about what I plug in, because I'm going to do square roots. So rather than just going up by 1 each time, I'll put in 0, I'll put in 1, I'll put in 4, and I'll put in 9. What's square root of 0? 0. Square root of 1, 1. Square root of 4, 2. Square root of 9, 3. That was why I picked those, right? Zero, 0, 1, 1, 1, 2, 3, 4, 1, 2. Oh, 9's off my screen, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9 would be here. Oops, 5, 6, 7, 8. Yeah, that's right. 9 would be here, up to 3. So again, make your graph smooth, but it'll stop here at 0. So this was just got, it's not the greatest of graphs, but it gives you the idea. It's going up to the right, but it's doing it slowly, isn't it? And this is why I said one of the reasons why you like graphs of functions. It gives you an idea of what's going on from a behavior standpoint. There's more than it just going up. It's going up, but it's going up at a slower rate the farther you go. All right, let's do this versus cube root of x. Again, I'll pick a few values that are good to start with. I'll put 0, 1, and 8. Cube root of 0 is 0. Cube root of 1 is 1, and I picked 8 because cube root of 8 is 2, right? I'm clever like that. All right. However, this is a cube root function, right? I only did positives for square root because we know we can't do square roots of negatives. Can we do cube roots of negatives, though? Yeah, sure can, right? So I can do cube root of -1 is going to give me what number when you cube it gives you -1? -1 does, right? If I do -8, what's the cube root of -8? -2, right? Because -2 times -2 times -2 gives you -8, right? So I can do cube roots of negatives, but I can't do square roots of negatives. Just like I can't do fourth roots of negatives, but I can do fifth roots. Notice there's that even odd thing again, right? So if we graph this one, 0, 0, 1, 1, 8, 2 is way over there. -1, -1. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 is off this graph a little bit. It's there. -8, -2. And it looks like this. But again, there's that even odd thing going on, right? I would expect an even root to behave like square root from a graph, an odd root to behave like cube root. So an 8th root would look like the first one. A 7th root would look like the second one. Does that make sense? Questions on either of those at all? All right. Let's do one more. And then we'll next time talk about doing some moving around of these graphs. The whole idea is to give us some basic shapes and then start playing around with how we can change those basic shapes. Last one, absolute value of x. All right. So again, remember, absolute value, if it's negative, it makes it positive. But if it's positive, it doesn't do anything, right? And if it's 0, it doesn't really do anything either. So if I just, again, pick some points, -3, -2, -1, 0, 1, 2, 3. When you put in -3, what do you get out? Put in -2, you get 2. Put in -1, you get 1, and then 0, 1, 2, 3, right? Everybody okay with that part? All right. Start plotting some points here. Now, on the other ones, I said that when we draw these things, we want to draw them smoothly. But something special happens for absolute value here when we draw it. Okay? Notice that nothing's really happening with these. If I put in positive numbers, notice it goes right one, up one each time, right? I get a graph of a line on this side, don't I? Same thing happens on this side. I'll get a graph of a line, but it's negative slope. What they're going to do is they're going to come to a point in the middle. So when we do graphing absolute value, we really get this V shape. I get a V that goes like that. Absolute value really is an example of something we refer to as a piecewise defined function, which we're going to do on Monday as well. Okay? But this basically gives us our library of functions to help us understand what graphs and more complicated things are going to be. So we're going to do that on Monday. We'll start playing around with, notice this one looks like square root of x, but we've multiplied it by something, right? The next one, this one looks like I've got an x squared, but I've added something, and we're going to play around with what that does to the graphs. Okay? And we'll also talk about how we graph piecewise things. All right. Have a good weekend, everybody. Don't forget you've got your homework due on Sunday on WebAssign.